Okay, our next speaker this morning is Joel Harris from the University of Utah. The title of his talk is Fluorescence Imaging of Single Molecule Retention Trajectories in Reverse Phase Chromatographic Particles. Okay, Joel.
Thanks a lot. It's a great pleasure to be here to honor Mary Worth on winning the Chromatography Forum of the Delaware Valley Dal Nogare Award. Mary and I go back a long time, back to the days of Purdue and before color photography was invented. Actually, this was, we overlapped in Fred Lytle's group for a couple of years. And of course, so Mary is back at Purdue, and the announcement that came in the alumni newsletter indicated that Mary's union with Purdue has come full circle. Of course, she is now the Fortune Professor of Chemistry. And I think if you have an endowed chair, you want it to be called the Fortune Chair, because that sort of implies good support. And she's back into some space that we shared as graduate students. And notice the smile and the dimples. You know that's the same person. So the question is, what about Purdue inspired Mary to think about topographical defects as a source of band broadening and reverse phase silica surfaces? Why were those important? And of course, if you live in Indiana, you have sort of these planar surfaces. I think this is a polishing mark on silica, right? It's a road, and there's occasionally other topographical defects, but all this area is where you get really good chromatographic performance. So. Yeah, potholes in the winter too, yes. All right, so today I'm going to tell you about some work that we've been doing that follows really on the pioneering efforts of Mary Worth, and that is to do fluorescence imaging of single molecules as they visit commercial reverse phase chromatographic particles. And so I'll talk a little bit about the challenges of imaging molecules within C18 silica, and then what we can do to characterize molecular transport. We're going to find those stuck molecules that Mary told us all about, and then we can also measure the moving molecule population and get diffusion rates, and then we can also look within the particle for spatial distributions and molecular resonance times. So that's where we're headed. So the experiment is close to what Christy Landis talked about, in the sense that we're doing single molecule imaging, but because we're looking at a particle that's resting on a glass cover slip, we can't confine our excitation just to the surface. So we actually have to allow a beam to go up through the sample. So we're actually imaging then with a particle that's resting on the surface and looking for the fluorescence of single molecules imaged back onto the detector. Our observation is confined by a depth of field on the order of a micron, where things are in sharp focus. It's a very high numerical aperture oil objective, so things come into sharp focus only within a narrow plane. And so in this particular case, the focal plane of the microscope is right at the glass cover slip particle interface, and you can see a little evidence of the particle boundary here because, in fact, to help adhesion of the particle to the surface, the glass slide is C18 derivatized, and so our dye molecules are quite hydrophobic, and they stick to that. So when we're in the plane of this glass cover slip, we see single molecules that are stuck to the C18 derivatized glass, but nothing much going on up in the particle. If we raise the focal plane up to the midpoint of the particle, notice that all of those molecules disappeared because they're out of our depth of field. On the other hand, we have molecules in sharp focus, and these clearly have to be inside the particle. So it's interesting that we can see diffraction-limited spots inside of something that we think of as highly scattering this porous particle. But you have to remember that the pore diameters within this, which represents the refractive index boundaries, are on the order of 10 nanometers or so, which is a 50th of the wavelength of the light. So when they're that small, they don't scatter very efficiently. Furthermore, the particles fill with solvent, so the refractive index difference between what's in the pores and the silica, surrounding silica, is relatively small. So we actually get diffraction-limited imaging inside of this porous beast. And that's kind of nice because it means that we can actually take commercial reverse phase particles and watch molecules visit them. And of course, that's, what they do, as at least I'm told by chromatographers such as yourself, as they elute down the column. They're visiting these particles and residing within them and then leaving. And then, of course, the time it takes for them to get in and out contributes to the resistance to mass transfer. So, yeah, can we see that? So here's a bright field image of a Zorbax 3-micron particle. There's a scale bar. And if we don't include our dye molecule, which is a rhodamine 6G variant with a tail, alkyl chain tail to increase its hydrophobicity, nobody's home. But then when we put in 5 picomolar of this dye molecule, we're going to actually be able to count molecules, measure their interparticle concentrations. We'll see them move around, and we can get diffusion coefficients. And we can also look at their lateral spatial distribution, of course, all within the depth of field, but all of our data is in X and Y. So here they are, and you can see them diffusing around, and from their motions, we can measure the diffusion coefficient, but every now and then, molecules get stuck. So that's a problem. And so, there are stuck molecules. What are we going to do? Of course, Mary's told us where these come from, and and this is just a fraction of the list of very important papers that where she and her students contributed to our knowledge of, understanding the sources of these strong interactions which occur at isolated silanols. And she did this with fluorescence correlation spectroscopy and also looking at the resonance times of single molecules on strong sites. So here's an example then of a recording of a molecule. There's a gap there in the baseline because at this arrow there's a molecule that got stuck. And this is within a small field of view on a planar silica model surface. But the nice thing also is that Mary then correlated this behavior with chromatographic retention data. She actually showed that these cationic dyes, like the kind we're using, similar to the structure she used, show these coulombic interactions with deprotonated silanols. So a lot of the interactions are, in fact, of ion exchange type, and that the silanols are found at topographical or defects and relationship to asymmetry. So the question we have within our trajectories, now that we're following a molecule moving in and out of the particle, what can we say about it? Well, the moving molecules are fairly easy to, when they can be identified, they're easy to understand. In fact, I'll show you this data again in a second, but the distance on average that they get away from their initial point goes up. The mean square displacement goes up with proportional to time. That's the Einstein diffusion equation. So we can characterize moving molecules quite easily, and we can take this mean square displacement and put it in a radial displacement probability distribution. We'll talk about that. So we do that by just literally tracking the locations of the molecules and then working up the data like this. And this would be the mean square displacement between frames. But the question is, what do stationary molecules do? Well, you wouldn't expect their displacement to grow with time, but is their mean square displacement measured as a radial probability? Is it 0? And sort of how long do they hang around? Furthermore, we have a problem is that molecules come in moving to get into the particle and then they get stuck. So we have a problem that trajectories include both motion and non-motion. So the question is, that we have to ask is, are we stuck or not stuck? And to define, in order to determine something about, whether a molecule is moving, we're going to actually first characterize the behavior of stationary molecules. And you can identify one because versus time, it doesn't make any progress. So that's good news. The question then is what's the mean square displacement between frames? It's definitely small, but it's not 0. And I can show you a trajectory of a stuck molecule. And you can see the molecule's apparent motion is actually due to the finite signal-to-noise ratio of our fluorescence data. So we're fitting this to a Gaussian function to determine the center location, much as Christy described. But then, and the motion, fitted out of this data is quite confined, but it also looks like a random walk. So in other words, it fits the same kind of probability distribution, even though it's not moving. But this then represents, our uncertainty in locating a molecule, and we have to detect motion above this apparent motion of a stuck molecule. And our localization error is on the order, the square root of the mean square displacement of stuck molecules, about 40 nanometers. And so if you want to ask the question, is a molecule moving, we know from hypothesis testing that you have to hypothesize the opposite and disprove it. So we hypothesize that it's stuck and disprove the null hypothesis. And so we have to use, to find moving molecules, we have to base the test on the stuck molecule population. So here that is. And we can go out to a critical value where there's less than a 5% chance if a molecule is out in this region in terms of an apparent step size that it was stationary. So there's a small error of identifying those, and that turns out to be about 64 nanometers. So if a molecule exceeds this, then we assume it's moving, and then we can use that to find moving molecules and then characterize their, how does their motion take them, how does the area which they'll be found increase with time, and that's linear, and the slope of that is 4 times the diffusion coefficient. If we, so there's a diffusion coefficient in the moving population. If we take the square root of that, that actually fits the single molecule displacement or single frame displacements with no change. This isn't fitted. That's just using the value from that slope into this distribution. It looks really good. The problem is our 64 nanometer threshold is a little, it's not so good at identifying stuck molecules, where you have to disprove that the molecule's moving. And so, in fact, to characterize a stuck molecule, we require that it not move for 2 frames, because then that takes this 10% probability that a molecule in this region it appears to be stuck but is actually moving. If it stays in here twice in a row and the chance of being there is random, then the moving molecule population, that would only represent a 1% error of type beta, where we've identified something as stuck when it was actually moving. So given that, we can go ahead and characterize first stuck events, and then we'll talk about the moving population. So the stuck events turn out to be 12% of the trajectories include at least one stuck event. In terms of the fraction of the actual frames where we watch motion, it's about a 1% chance. What I've done here is to histogram the stuck event times, and it's exponential with a pretty reasonable fit, with a short time that characterizes the greatest of this population, and then something that's out at a quarter of a second, so out on this tail. I think what's more interesting is the spatial distribution, and that is that, so this is the histogram in space. So we have and we've set this up within areas that we can resolve. We know what our resolution is, 64 nanometers. So we break up the locations into, these 64 nanometer spots, and then there's a whole bunch of fairly low probability, low numbers of revisited sites, right? That's down in the blue. But these ones that are above 5 per site are all anomalous. And so, one of these resolved sites was visited something like 27 times. So these are the bad actors because they represent a significant defect with a high, actually quite high energy of interaction. This proves sort of the anomaly, the sites that aren't visited very frequently. So this is number of sites per visit. This is the full probability distribution, and this is blown up, where we, this starting about here and down. And you can see this fits actually as a Poisson distribution. This is the same one that Giddings and Davis used to determine the probability of molecules overlapping in chromatography. Well, this is the probability that spots overlap out of a random distribution, and that fits nicely a Poisson for these small, small numbers of visits, right? That's this axis. And so, I mean, that looks like, I mean, that fits a model where we're just talking about chance overlap of a fairly large number of randomly distributed sites. It fits pretty well up to about 4 sites per visit, and then notice that all of, here's the theory, it's at 0, and all of these sites that go up to this 27, these specific sites look like bad actors. What's interesting is these sites account for 112 of the 345 stuck events. And what's even worse is that in this lower visits per site, the sort of random population, there's only a 3% chance that they're in the long-lived, the ones that hang around a long time. And that yet in this group, there's like a 24% chance that you'll see a long-lived interaction. And of course, that's bad in terms of chromatography. And so what really matters to separations is the interparticle resonance times and the dispersion in those, right? Because that's what's going to lead to peak tailing. And so in fact, what I've done here is the black dots are the resonance times within the particle, but I have to qualify this is within our depth of field, and that doesn't include the entire particle. So here's all of them, and if we sort those out and just include trajectories that happen to have a stuck event within them, then notice how much longer the resonance times are and how much longer tailed they are. So the trajectories with stuck events, lead to almost an average of 1 second, 0.8 of a second resonance times within our depth of field. Those with no stuck events are 1/10 of that, and all trajectories are, of course, a little in between. What's interesting is we actually did a model. We have, of course, measured the diffusion coefficient. I showed you that with the slope of that curve. And that diffusion coefficient we can use to predict the time, on average, that a molecule will visit this region before it leaves. So we ran a Monte Carlo simulation using the diffusion coefficient in a little 3D model, and we used that with no fitting parameters to characterize the resonance times of moving molecules. And look at that. I mean, in other words, no adjustable parameters other than the number of events, which is just scaling. So this just comes from a measured diffusion coefficient, which then says that, within this region, if a molecule isn't stuck, then it's diffusing quite homogeneously. So the transport, within this particle looks totally homogeneous with exception of strong adsorption events. So with that, the other question is, well, is there other evidence of a homogeneous distribution? The other thing we can do is we can localize, we know where the center of the particle is, and we can measure the radial distribution of molecules with respect to the particle center just by locating them within all the movies. And then that's the data are the black dots, and the red are from our Monte Carlo simulation. And what you really see, and this is really relates to our experimental geometry, is that the probability goes up linearly with distance from the center, and that's because this is relatively thin, on the order of a little less than a micron. But then, in other words, we gain area as 2 pi RdR, and so in other words, this just goes up linearly. But the agreement between both the diffusing molecules behavior and the homogeneous distribution says, well, certainly, in other words, the molecules get everywhere within this particle center region. They can get there, and the probability is predictable. On the other hand, we can take a step into the world of theoretical predictions. Since this agreement was good for the depth of field, we can certainly take the same diffusion coefficients and estimate what the resonance times will be for throughout this fully porous particle. And the distribution versus radial distance now is quadratic, of course, because these shells have, as you go out in R, have 4 pi r squared dr volume. So the probability is going up quadratically. But what's really interesting, of course, is that, here the resonance time is truncated because a molecule can simply diffuse out of our depth of field. Here, it has to actually get out of the particle. And look at what happens to the resonance times. They go up by a factor of 10 on this tail. So, in other words, this still drops relatively fast, but this tail, which is molecules getting, all the way into the center and taking forever to get back out, is clearly a problem. And of course, we know how that's solved. Ron Majors has talked about it, and that is that you use core shell material or pore shell or pellicular columns, whatever. Something with a solid core and a a porous outer region. And so what I've got here, this is just average fluorescence intensity for a little period of time from an Agilent pore shell 120, and these are just intensity maps, not single molecule, but you can see this is some stuck single molecules. And so here's the fully porous, here's the porous shell material, and so clearly we can image the fact that this core is, doesn't have any molecules in it. This actually sort of indicates how bad our actual resolution is. If we go to single molecule, identifying where the single molecules are and using that to map the radial probability distribution, you see a nice jump at a radius of ½ micron. And then intensity goes up and then back down at the outer boundary. So that looks good. And this is simulating with a random walk. And similarly, if we just take the moving population in this, we also, again, from the diffusion coefficient, we get a nice model as to what the resonance times are. And they've shortened up by about a factor of 2. And you can see that. So here's the resonance times if we remove the stuck molecules. But the bad news is that when we include the stuck molecules in the distribution, these are much too close. So it looks like the stuck events are overwhelming the diffusional, the benefits of having shorter diffusional paths. And so we can test that, of course, by mapping the stuck molecules again. So here's the 3 micron ODS full porous material. You notice there is a greater probability for molecules to be on the outside than the inside, and that's because there's more, there's a greater chance for them to just come in and visit, come back out. So that's all in the radial probability distribution. But this, these stuck events still get up to numbers on the order of like 10 that we had before. But look at the number of revisited stuck molecule sites in this pore shell material. Some of them got up in the 40s. So clearly there's an issue of the density of strong silanol sites in this. And this dye is actually dye I, the same molecule that Mary had used to study planar C18 surfaces. And it's it really goes and seeks strong silanol sites. So just like Mary said, these are important, and geometry won't solve that problem. Of course, you can treat the surface to try to reduce those, and so recently we got some Zorbac C8 end-capped versus non-end-capped from Agilent. They were kind to donate this to us, and you can really see the impact of this on stuck sites and revisits and so forth. This looks quite homogeneous with, in fact, only a few that would be above a Poisson distribution. The non-end-capped is just loaded with stuck sites. So for us, this is great. Gives us something to publish. But I know you wouldn't want this happening in your column. So the stuck times, interesting. The stuck times are shorter by about a factor of 2. But more importantly, there's a whole lot more of them in the non-end-capped material. And what's interesting is that the short resonance times, the resonance times are a little longer than with the R18 single chain. This dye has 2 chains to make it a little more hydrophobic. And you notice they're actually indistinguishable, but the long ones, it's the long events that are more energetic as well as much greater in number. So let me finish up with, following the pioneering work of Mary, we've investigated trajectories of single molecules visiting commercial reverse phase silica. We can measure diffusion rates of moving molecules and use that to predict resonance times of molecules that are moving within the particle. But then molecules sticking to strong adsorption sites play a critical role in governing the retention heterogeneity, and it's just what Mary showed in her beautiful work. And depth of field right now is a limitation. We really like to watch a molecule visit the entire particle, and we've got plans for that. We're waiting to see if we can get some funding to do it, but it's certainly possible. You can put a little bit of astigmatism into the image that's going to the camera, and you can detect whether a molecule is above or below the focal plane, and you can use that information to drive a Z stage. So you wouldn't do this with multiple molecules at once. We go to lower concentrations, so we're actually only following a single molecule at once. But there's a chance of maybe doing 3D tracking of molecules within these particles. So the work was done by Justin Cooper and Eric Peterson. The funding came from the Department of Energy, and Agilent actually gave us a university research grant to support Justin's work. And of course, also want to thank our award winner and Mary Worth and you for your attention.
Hey, Joel, do we have any questions?
Eric?
I was curious about the revisited sites. We found something similar to that. Load them up with multiple molecules. So we're, when topographical defect, chances of revisiting chances would be really small if there weren't many sites around it.
Yeah, right. So you lengthen the visit time because you may release, but you're going to find the other part of the site.
If you just had one scrum on your surface
Right.
that something had to find on the time scale of your measurement, you're probably not going to find it over and over again. You should have many in the same
You got a
region.
patch.
You
So,
have a patch.
right.
Right.
But it also may
They all behave the same with the same absorption.
it also may account for the for also the longer times at those sites. Maybe you don't think so?
The same, no matter.
Okay. Well, I was just thinking that if it found the site, it'd be more likely to find a larger site again. So that, and if that happens on a time scale short compared to our framing rate, it may lengthen the apparent time. You didn't see that. Okay. Yes.
Do you suspect that that's because of difficulty in bonding that site, or is it because there's likely to be metals making it a hotspot?
No, actually, yeah, Mary showed it that you can make most of these go away by just treating the silica at really high temperatures and annealing out the topographical defects. So, but you talked to Mary about that. So. Yes.
I missed the beginning of the talk. Was it for small molecules or large molecules?
These are dye molecules, but both had one case. One had a one tail, the other. They have a long aliphatic tail on them to increase their residence time, to increase their.
That's small molecules.
Yeah, they're still the small molecules, not proteins or anything like that. No.
From all these histograms, can we extrapolate to absorption rate constant, for instance, that you can estimate?
Yeah, I think the problem is modeling that right now the diffusion is on the surface of the material because the retention time, for the chromatographers, our capacity factor is on the order of about 500. So, in other words, these are, and that's to get long enough residence times that we can follow a molecule. If it's spent, if we decrease the retention, then our visits would be so much faster and we couldn't track them because our framing rate's about, we can go down to 30 milliseconds. And we're now doing FCS down to at kilohertz rates, so milliseconds within the particle. But, and we can go to somewhat more realistic retention conditions. But right now, these are strongly retained. So, yeah.
For your planned 3D tracking, it sounds like you're going to use instrumental feedback, and I wondered if you thought of using this new phase mask technology and imaging in the foyer plane might allow you to be. We haven't tried it yet. We're just planning to try it.
Yeah, I don't know. These distances are so long, we actually have to move the focal plane. Yeah, so we can't. I like, if you're working in something like 100, 200 nanometer kind of, then it would be great. But we actually literally have to move the stage because to track. It's going to be a challenge, but it's a fun one.